everyone, today we're going to talk about similar matrices. And why do we want to talk about similar matrices? Well, it turns out if A is similar to B, that we denote with this little squiggly thing, we can actually deduce a lot of things about B. It's like members of the same family. A and B are both different and unique matrices, but they share a lot of important characteristics or properties. For instance, two similar matrices share the same rank, they share the same trace, they share the same determinant, and most importantly, they share the same eigenvalues. And the definition for a similar matrix is A and B are similar if we can find an invertible matrix, and I'll denote this invertible matrix P, such that our B matrix here is equal to P inverse A P. So if we can find this invertible matrix P, and we can connect A and B in this way, that we take P inverse AP is equal to B, then we know that A and B are similar. And now this actually makes us understand a lot about B and A too, and we're going to prove all of these things. One word of caution though is although the eigenvalues are the same, often not the case for eigenvectors. So eigenvectors are often different. So to use an example of this, we might have the matrix A is equal to 4, 2, 0, 1, and the matrix B be equal to 3, 1, 2, 2. And again, we can kind of see here. So for both of these matrices, they have linearly independent columns, which means that the rank of A is equal to 2, and the rank of B is equal to 2. Next, we can look at the trace. So the trace of A is kind of summing up the elements on the diagonal. So in this case, that's going to be 5. And the trace of B is also summing up the elements on the diagonal, which in this case is going to be 5. Then we can keep on going. The determinant of A is going to be AD minus BC, so in that case is going to be 4. And also the determinant of B is going to be also 6 minus 2, which is equal to 4. And from this, we can also then deduce the eigenvalues. That we know that lambda 1 for A is going to be 4, lambda 2 is going to be 1, and similarly for B, we have the same eigenvalues. However, if you solve for the eigenvectors, so this was the kind of word of caution, the first eigenvector of A is going to be 1, 0, and the second one is going to be negative 2, 3, while for B, V1 is going to be 1, 1, and V2 is going to be negative 1, 2. So those are not the same. But if we look at all of these other things, all of these other properties, we can see that they are the same. And what's really cool too is that if we know that A and B are similar, we also know that their matrix exponentials are also similar. Because if we know that B is equal to P inverse A P, and then I want to ask, okay, what is B to some power n? Well, this is just going to take this part right here, and we're going to multiply it n times. But what we can see is that at these kind of junctions, so we're doing this n times right here, but we can see it at each junction right here, we get P inverse. And because P is invertible, and P times its inverse, or a matrix times its inverse, this will just turn out to be the identity matrix. And since the identity matrix times, for example, A will just be A, it actually turns out that we can just connect all of these A's together that we have all the way to the end. And the only ones that are left, the only P's that are left are the first P inverse and the last P inverse, which means that we end up with P inverse A n times P. And then we can see that B to the n is actually then similar to A to the n, because yet again, we have the same matrix, we have some matrix here that connects the two of them. And another thing that's cool is that these properties go both ways. That if A is similar to B, we also automatically know that B is similar to A. And why is that? Well, if we have this matrix P inverse times A times P, if we multiply by P on the left to get rid of this P for the A side, we're going to get PB is equal to AP. And then again, if I multiply by P inverse here on the right, we're going to get PB, P inverse is equal to A. Now I'm just going to rewrite that in a form that we're kind of more familiar with. I'm just going to put A on the left side. So we have PB, P inverse. And it's not quite what we had here, because then we're started with P inverse. But I can just define a new matrix. I'm just going to say, okay, well, Q is going to be P inverse. And that means that Q inverse is going to be equal to P inverse inverse, which, if you take the inverse 2 times, it's just going to be P. And then I can write then P, which is Q inverse, right here. So P will be Q inverse times B times Q. And again, because I've found a matrix, it doesn't have to be the same as for B, but because I found one matrix that is invertible and that connects A and B in this way, I can say that indeed B and A are similar. So now I want to prove to you why the trace of A is equal to the trace of B. So again, I'm going to write down our important connection between these two. And then I'm just going to say, well, then the trace of B is going to be the trace of P inverse AP. But then we have these properties of the trace that says that, well, the trace of AB is equal to the trace of BA. So in this case, I can just reorder and say that this must mean that the trace, so if I kind of do a little parentheses here, that means that P inverse must be the same. And then we can group these two P's, they just become the identity, and then we get the trace of A. So indeed, the trace of B is equal to the trace of A. Next up is the determinant of A is equal to the determinant of B. Again, I'm going to use that the determinant of B is equal to the determinant of P inverse AP. And then I'll use the property that the determinant of ABC is just going to be the determinant of A times the determinant of B times the determinant of C. And this means that we get the determinant of P inverse times the determinant of A times the determinant of P. And now I can kind of just reorder these as I want. So I'm going to put the P inverse on the other side here, because multiplication, we can do it in any order we want, because these are just numbers. Then I would get the determinant of A times the determinant of P inverse times the determinant of P. And again here we can kind of go the other way, that we can kind of combine these two determinant statements to say, hey, this is the determinant of A times the determinant of P inverse P. But now this will just become the identity, and the determinant of the identity is always 1. So this actually comes out to be as the determinant of A. So therefore, these two things are indeed equal. Then I want to show to you, why are the eigenvalues of A equal to the eigenvalues of B? Well, if we know that V is an eigenvector of A, then we know that AV is equal to lambda V. And now again, we don't want to say that V is the same for A and B, because the eigenvectors don't have to be the same. I just want to say that the eigenvalue is the same. I.e., if I can have an eigenvector, I know that I will find another corresponding eigenvector for B with the same eigenvalue. And to do this, I'm going to do a little trick. Since I know that P is invertible, I can say that, well, A times P inverse times V is going to be the same thing as above, because this is just going to turn out to be A times the identity V, which is going to turn into A times V, which is turning into lambda V. So this little thing right here is just a little trick to get P and P inverse into the picture. And then finally, because we know that B is equal to P inverse AP, now we can see that we kind of have this AP here and the AP here, so I'll just multiply by P inverse on the left. So I get P inverse A, P inverse V, and since I multiplied on the left of P inverse, I need to do that on the right-hand side too. But since lambda is just a value, I'll just keep that on the front and then do P inverse V. And then, since we said that B is all of this business here, which we can find right here, I'll use substitute and say that B, P inverse V, is equal to lambda P inverse V. And what do you know? Right here, that I'm highlighting in yellow, this is just another vector. This is P inverse V. And that's just another vector, and here we can see we have lambda times that vector. So indeed, P minus 1V must be an eigenvector of B with the eigenvalue lambda, which was the same as for A. So it has the same eigenvalue as A. The eigenvector is different, but the eigenvalue is the same. And finally, I want to show to you why rank of A is equal to the rank of B. So if we start with B again, we can convert it to our different form where we say PB is equal to AP. And then I can ask, okay, what is the rank of PB? Well, from what we've learned before is that rank of PB must be less than or equal to the minimum of the rank of P and the rank of B. However, we are in a pretty special spot here. Because P is invertible, we're actually not changing the output dimension of B. That actually means that since P is invertible, we can say that rank of PB is equal to the rank of B. And then similarly, we can say, well, okay, the rank of AP is going to be equal to the rank of A, since again, P is invertible. Then, since PB is equal to AP, we know that the rank of PB is equal to the rank of AP. And then since rank PB is equal to rank of B, and rank of AP is equal to rank of A, we conclude that indeed the ranks are the same. So to conclude, similar matrices are connected by this invertible matrix P in this form right here. And it's important because similar matrices kind of are in the same matrix family. They share the same rank, trace, determinant, eigenvalues, which makes them have similar characteristics and will help us understand maybe different types of matrices. Thank you for watching, and in the next video, we'll talk about how this relates to a very important concept called diagonalization. See you there.